What's up guys, this is Massey. Welcome to another video. In this video I want to show you how to find out the solubility of FeOH3 with KSP 4 times 10 to the power of negative 38 in each of the following solution. Part A, water. Part B, a solution buffered at pH equals to 5. And C, a solution buffered at pH equals to 11. We'll start with the first one. When you are dealing with water, pH is 7 and the concentration of hydroxide ion is 10 to the power of negative 7 mole per liter already. Now when we are dealing with FeOH3, it's definitely in solid form. When it is dissolved, it's going to produce Fe3 plus 3OH minus, both of them in aqueous solution. So initially, nothing here, and here we have 10 to the power of negative 7 before dissolving. After dissolving, so change is going to be negative x plus 3x. Why 3x? Because here we have 3 coefficient, here we have 1, and here we have 1 as well. So equilibrium, we don't write it for solid, here is going to be 0 plus xx, 10 to the power of negative 7 plus 3x. So KSP 4 times 10 to the power of negative 38 equals to concentration of Fe3 plus times OH minus to the power of 3. So the concentration of Fe is x, the concentration of hydroxide is 10 to the power of negative 7 plus 3x to the power of 3. So 4 times 10 to the power of negative 38 equals to x times 10 to the power of negative 7 plus 3x will be, if you solve it like that, it's going to be complicated. But here, since KSP is small and we have 10 to the power of negative 7, we can say that we can neglect 3x comparing to 10 to the power of negative x. So I'm going to simplify. We assume that 3x is much smaller than 10 to the power of negative 7. So I neglected that one. The power of 3. So 4 times 10 to the power of negative 38 equals to x times 10 to the power of negative 21. So x will be 4 times 10 to the power of negative 17 mole per liter. That's the molar concentration of FeOH3 in water. Now let's do the part B. In part B, solution buffered at pH 5. It means that the concentration of H is 10 to the power of negative 5 and the concentration of hydroxide ion is going to be 10 to the power of negative 9, because 9 plus 5 is 14 mole per liter. So we can say again FeOH3 is going to give us that solid Fe3 plus 3OH minus nothing in the initial 0, and here we have the concentration is 1 times 10 to the power of negative 9, or just 10 to the power of negative 9. That's I. Change, I stable. Change is going to be negative x, positive 3x. Equilibrium, we don't write it for solids. This one is x, this one is 10 to the power of negative 9 plus 3x. So KSP, which is 4 times 10 to the power of negative 38, equals to x times 10 to the power of negative 9 plus 3x to the power of 3. That's going to be x times 27x cubed, which is going to be 27x to the power of 4, which will be 4 times 10 to the power of negative 38. So x to the power of 4 will be 4 times 10 to the power of negative 38 divided by 27. That will be 4 divided by 27, negative 38 to the power of 125. So x will be 1.96 times 10 to the power of negative 10. So that's going to be the molar solubility if we assume that 3x is much larger than 10 to the power of negative 9. Now let's 10 to the power of negative 9 is much greater than 3x. Now let's do it the other way around. Let's don't consider 3x and consider 10 to the power of negative 9. So it's going to be 4 times 10 to the power of negative 38 equals to x times 10 to the power of negative 9 to the power of 3. So it's going to be 4 times 10 to the power of negative 38, x times 10 to the power of negative 27. So x will be 4 times 10 to the power of negative 11. So now I solve it in two different ways. As you compare these two numbers, compared to 10 to the power of negative 9, it means that the second one, the second assumption, which we said 10 to the power of negative 9 is greater than 3x, is a valid assumption. The previous one, which I wrote it here, consider 3x is much larger than 10 to the power of negative 9, which it was a wrong assumption. Remember, most of the time you need to double check your assumption, and that's going to be the right assumption. So that's going to be the solubility, which is 4 times 10 to the power of negative 11. Now let's do part C. In part C, we have a solution buffered at pH equals to 11. So it means that pH equals to 11. It means that the concentration of proton is 10 to the power of negative 11. So OH is 10 to the power of negative 3. So then again, when you use ice table, you're going to have FeOH3. It's going to give us Fe3 plus 3 OH minus. In this case, you're going to have X for Fe, and for 3 OH is going to have 10 to the power of negative 3 plus 3x. So obviously, because of the value of KSP, we can say that 10 to the power of negative 3 is much greater than x. So we can say 10 to the power of negative 3 is much greater than 3x. So we keep this part and neglect 3x. So KSP will be equal to 4 times 10 to the power of negative 38 equals to x times 10 to the power of negative 3 to the power of 3. That will be x equals to 4 times 10 to the power of negative 38 over 10 to the power of negative 9. So that will be 4 times 10 to the power of negative 29 mole per liter. So that's the solubility of FeOH3. As you see here, 10 to the power of negative 3 is much greater than 4 times 10 to the power of negative 29. So it means that we had a valid assumption. So that's how we find out the solubility in different solutions. I hope you enjoyed this video. Please leave me a comment if you have any question. Please don't forget to subscribe this channel. You can have access to many other videos regarding solubility and other topics in chemistry, physics, and math. Thank you for watching and have a great day.